We are at the top of the hour, and thank you everybody who joined. This is the first virtual MPLS interim meeting that we're having after IETF 119. And the agenda today is pretty brief. We're going to talk about the feedback on an M&A MPLS network action implementation that we've been working on in the working group. And for this, I think Fabian and Michael have prepared some material and they will be sharing. Myself, Tarek, as well as Tony and Nick will be chairing this interim. We are going to take some minutes on the Hedge doc. I'll leave a link where we can contribute if you have the bandwidth. And let me, before I pass it on to Fabian, let me ask if Tony and Nick want to add anything else I might have dropped.
So nothing from my side. I'm still fighting a bit with the tool.
Yeah, sorry, go ahead.
No comments.
Thank you. I'll just pass the link for the minutes taker where we're logging the minutes in the chat. And Fabian, is the material uploaded? I don't think I saw the material being uploaded.
Not yet. Can I upload that myself, or should I send that to someone?
You can share your. You can send a request to share, I think, your screen itself.
Oh yeah, I can do that.
Okay.
I thought, do you need the slides as a PDF file beforehand, or should I just share my screen?
I think you can share your screen, but it's also a good idea to upload using the the page for the virtual interim meeting session. I can pass the link for that if you're missing it.
I guess it's the propose slides button there.
Yeah,
and I can just upload in there. Yeah. Okay. Yeah. Just a second. Okay, should be uploaded. I hope it was the correct set of slides, but I think so.
Okay. Can you hear me, Fabian?
Yes, I can hear you.
Okay, I think you can click on the button. I'm not seeing any slides yet.
Okay, I started a screen share, but did you get the uploaded slides too, or?
Yeah, I can. Yeah, I cannot check if the. Let me double check. But for now, I can see what you're sharing myself, and I believe others as well. So we can get started.
Okay. I will just turn my video on so that you got a face to the talk. Okay. So my name is Fabian Ile. I'm a PhD student at the University of Tübingen in Germany. And there we implemented the M&A framework in its current state on the Intel Tofino in P4. So I will talk and discuss today about our implementation experience with that. Here's for today's agenda. I will first provide you with some background information on M&A and the relevant drafts so that we are all on the same page. Then I will talk about mutable data, including PSD. I will present our proposed operation modes. And finally, I will describe the implemented pipeline in a bit more detail and show you an implemented example network action. Now, before we start, here's a legend for this talk. So you will find those colored bookmarks and circles on each slide. And they indicate if the content is from the current IETF drafts in green, if it's a proposal by us in blue, or a topic for discussion in red. So if you see a red circle, we can have a discussion there, but of course you can ask at any time or after the presentation. So here's the motivation, not for the M&A framework, but for this work. And for M&A to be successful, it must be efficiently implementable in hardware, because we've seen similar cases with IPv6 extension headers, where packets that contain multiple of those headers are often dropped by many routers in transit. And the reason there is that at scale, IPv6 extension headers are not that trivial to implement in hardware. So we need to find out if the M&A encoding works on hardware. And we in Tübingen use the Intel Tofino as a reference architecture for hardware implementations. And there we follow the paradigm that if it works on the Intel Tofino, it will most likely also work across other more powerful or vendor-specific hardware. So now the questions behind this work are if the IETF M&A encoding can be implemented efficiently on hardware, what the challenges are, and later then if we should use PSD or not. Now first some background to get started. The M&A framework is a general mechanism for transmitting, processing, and executing predefined network actions. And for that purpose, a new generalized head encoding is introduced that defines how to encode network actions and their data. And this encoding is called the network action substack, short NAS, and is basically a stack of related LSEs containing network actions and their data, which is inserted into the MPLS stack. So now, what does such a NAS look like? Basically, it's a BSPL entry followed by network actions and their data. And this BSPL is called the NAS indicator. Then for the rest of the NAS, the traditional encoding is redefined to encode network actions. So we do not have the traditional label traffic class TTL encoding, but we have rather 3 different new encodings. There we have the mandatory initial opcode, which contains an opcode, some data and configuration parameters, and a length field. Then we have the optional subsequent opcode type and the optional ancillary data entry type. Here we have some examples for valid NAS according to the IETF draft. That's the absolute minimum we can have with only a single initial opcode. Then we can have multiple subsequent opcodes, and note the length fields here. That's the example we've seen on the slide before. And we can have one larger NAS with different numbers of ancillary data inserted into the stack. Now they all have in common that there's no ancillary data after the initial opcode LSE. So we cannot have ancillary data here. And that's because right now it's not allowed in the encoding, and there's also no length field for this purpose. And this brings us to our first discussion point, because during implementation, we ask ourselves if we cannot move the configuration parameters of the initial opcode, so this part here, into the TTL field of the BSPL and eliminate that encoding type, because that basically simplifies the encoding and saves us 8 bits. And as I said before, the initial opcode cannot carry ancillary data. So let's say if we only have a single action in a packet that requires ancillary data LSEs, then we have to put in an initial opcode LSE that is not used, because there can be no ancillary data and we have to waste one LSE. Also, if we look at defining those network actions, we always have to keep in mind to have either 2 different versions or 2 definitions of each network action, meaning for each LSE type, or we have to constrain network actions in the definition and say that the action is only valid for one type. And therefore, we think it would be better to eliminate this encoding type, the initial opcode type, completely and move the flags into the BSPL and only work with opcode LSEs and AD LSEs. But we don't know if there are any other implications with redefining the values in a BSPL, because I think that those fields, the TTL, is not really used, but maybe somebody can comment on that. That would be great at this point.
Yeah, so there's actually some text in the draft. The TTL field is absolutely necessary in the format A LSC.
Okay. What's the reason behind that?
So we have a case at the, I'm sorry, I don't remember the details at this point. Yeah, but if you dig up the draft, it talks about it. And Stuart's jumping in to remind me.
What I was going to say is that there is some hardware, quite ancient hardware, that may pre-decrement and check the TTL, so you may not get the TTL value you expected.
But is a TTL value really necessary for a BSPL entry? Or is that, again, some backward compatibility thing then if we want to deploy that and we will have problems with that?
There is some hardware. I mean, it depends on, we have to be able to deal with any hardware implementation, right? And some hardware pre-processed the TTL before it realized that it shouldn't. I had this problem in pseudowire designs a long time ago.
Okay, so I draw the conclusion that we cannot do this in this case then. All right.
Feel free to start a discussion on the mailing list. Maybe, first check the draft, see the text there, and then feel free to start a discussion if you don't agree with the text.
Yes, I will read the draft again and search for some more information. Okay.
One follow-up on this from my side. If I remember correctly, at the penultimate hop, there was a possibility that the special purpose label would show up as the top label after popping all the transport labels. So in that case, we don't want to play with the TTL. But I'll double check. We discussed that in the past, but that was just something that came up to my mind.
Okay, thank you. Then I will just continue. So another concept introduced in another separate draft is post-stack data. And post-stack data is located, as the name says, below the MPLS stack. So with some offset or directly below the MPLS stack. And in the draft, the presence of PSD is indicated by a bit in the initial opcode of an in-stack NAS. And right now in this draft, the reserved bit is proposed, but there are ongoing discussions whether another bit or an opcode should be used. And at least in my experience with the implementation now, a bit is way easier to implement because we can in P4 easily check it during parsing. If we would have an opcode, we would have to check every opcode in the stack during parsing. But the position of the bit could be changed, of course, if we want to keep the reserved bit in this case. You see, here's a red circle, so we can discuss about this now, but maybe it's better to discuss it afterwards or move it to the mailing list, as I think there were already some discussions about that. So I see a raised hand in the Meet Echo tool by Tony.
Tony, yeah, I think, yeah, I'm not sure if Tony had it by mistake.
Ah, okay. No? Okay, so I move the discussion to the end. Okay, there's another hand now.
Yeah, actually, I think the current proposal is to have a reserve bit in the not in the initial opcode, but it's I think it's part of the reserved bits, right?
Yes, exactly. Yeah. It's this reserved bit. If you look at the encoding before, it's a single reserved bit.
Yeah.
And now it's the P bit. Or
yeah. Right. Yeah, just for clarification. Thank you.
Yeah. Okay, so in the draft, we have another encoding introduced. It follows basically the same principle as a NAS, but the MPLS requirements like the bottom of stack bit are gone, but we have that first nibble and diversion field. But the principle is the same. We have a post-stack network action top header that indicates the beginning of the PSD, and then we have the post-stack network action header where we again can define opcodes data and the length. Okay, there are two hands again. I'll just ask if there's any question on that.
Yeah, Jimmy dropped, so Greg is at the top of the queue. Go ahead.
Yes, thank you. I have a clarification question. So in the previous slide, you referred to the in the draft PSD encapsulation, but the working group draft does not define any PSD encapsulation.
This is actually in this draft here below, not in the header encoding draft, but there's a separate draft for post-stack encoding.
Yes, but this is individual draft. So it's not being sufficiently discussed and considered. So I don't know how much of really relevance it has to their discussion of M&A, because it's only one possible way. And so as working group draft can change, so this one is even more so.
Yes, that's true. We just used that draft, even though it's not a working group draft, as a reference to read about PSD and to search for possibilities how to implement PSD. And we based our implementation for now on this, but don't take that as a production-ready implementation or production-ready post-stack data encoding.
Okay, thank you.
Okay, so next point is different scopes in the NAS encoding. And that's an important concept for us, because a scope tells where network action should be processed. And right now there are three different scopes: the hop-by-hop scope, the select scope, and the ingress to egress scope. And there should be only one NAS per scope per hop allowed, and a NAS must not be on top of the stack. And if a node exposes one to the top, it must therefore also pop the NAS. And now in our work, we only look at segment routing with MPLS, as normal label switching is quite easier to do. And here we have a potentially larger MPLS stack with multiple NAS. So now in segment routing, the node that pushes the MPLS stack at the ingress must ensure that each node on the path can read its network actions. And for that purpose, those nodes signal the readable label depth, the RLD, to the ingress node. And the RLD is the number of LSEs the node can read without performance impact. So then the ingress nodes takes care that the NAS is placed within readable label depth for each node, and therefore may have to place multiple copies of a NAS in the stack. And here you see an example of such an MPLS stack with having two hop-by-hop NAS copies. And we refer to this as hop-by-hop NAS replication in the following. So one more aspect that we find is important is mutable data. And with mutable data, we mean data where the value changes during packet forwarding on a path. An example for this is the collection of telemetry data along a path. For example, collecting node IDs doing some path tracing or timestamps. And that information must be kept and updated along the path. So for backward compatibility, only the last 8 bits of an LSE are mutable. And that's because legacy devices might hash the MPLS label for load balancing, and we do not want to change that. So only those bits in the LSEs are mutable. Now the challenge is, how can we use more than those 8 bits for mutable data if we need mutable data? And how can we carry mutable data in the MPLS stack with the hop-by-hop NAS replication we've seen before? And there's another hand by Greg.
Yes, thank you. I'm not sure that I know that any use case that been acknowledged that requires mutable data support, less mutable data being part of their label stack. So although it might be interesting for research, but so far there is not agreement, as I understand, that we have a use case that does require mutable data being supported, especially in the label stack.
Yes, I'm aware of that, because for the mentioned collecting telemetry data here, we can, for example, just use the direct export function of IOAM, for example. But as you said, for research, this topic is of interest because it has challenges in it. And as you will see later, in-stack data is quite easier to do without mutable data.
Yes, if we talk about the telemetry data collection in a data packet itself, then as I understand it, the proposal is to use not in-stack ancillary data, but post-stack data. So then the mutable will be post-stack data, not in-stack data still.
Yes, we will. That's exactly what follows in the next slides. So, stay tuned.
Yeah, no. What I'm saying is that then probably the green should go for red flag for discussion, because it's currently working group documents do not require mutable data in stack.
Yes, all right. So here's now an example that illustrates the problem with hop-by-hop NAS replication and mutable data, but with the background that for this, we take in-stack data mutable. So if that's not directly in the draft, that's just an example of what a problem would be here. Okay, so we have an example network with some transit nodes, an ingress node that pushes the stack, and an egress node. And we have different RLDs on the path and the M&A incapable node. So now the ingress node pushes the stack, places 2 hop-by-hop copies in it, and in green you can see the set data bits. Now node A receives that packet, has the hop-by-hop NAS in readable label depth, adds some data, and forwards the packet according to label 60 to node B. Same happens at node B. Node B adds some data, forwards to label 70, pops the label, now has the hop-by-hop NAS at the top, and therefore has to pop the hop-by-hop NAS as well. And that's where we would have a problem if we are doing mutable data in stack, because we don't know what to do with the already with the mutable data. And at the moment, it's not quite clear how to find such a conflict and how to resolve it if we're doing that, because in theory, we would have to copy the data down, but the NAS copy is not within our RLD. So we wanted to find a way that prevents those conflicts altogether. Yes, Greg, please.
So I have to come again to this. You set a use case as a problem that needs to be addressed that doesn't seem to be really grounded on any use case that is listed in a working group document that documented use cases. So it's a draft IETF, MPLS, M&A use cases. So I'm really, again, that might be interesting challenge to resolve, but how practical it is.
How about we just take this as a point for future requirements?
Yes, future requirements, that's fine, I agree. But again, then the consideration, or at least from what I understand, the mutable data is supposed to be post-stack data. So there is no use case for in-stack data, unless I'm missing something.
Yes, you can see that kind of as a motivation for post-stack data, why we should do post-stack. So you can see yourself confirmed in the use case drafts with this example. I'm not saying that we should do this or that this should be in a use case draft.
Yeah, I think even though we don't have a use case for mutable data in ISD now, but that it doesn't mean in the future we can't. As a general solution, I think we do need to consider this situation and find a solution for it, because we cannot exclude these possibilities, right?
Again, we can agree, and I don't argue, that if and when we need mutable data, then post-stack data seems like a appropriate solution, but let's first discuss the use case. Thank you.
So the point's been made. Let's move on.
Yes. Okay, so quick conclusion. With the hop-by-hop label replication, we have multiple copies of the hop-by-hop NAS in the stack. That leads on the one hand to larger stacks, and on the other hand makes the handling of mutable data difficult in stack. And that's why we propose the concept of hop-by-hop NAS preservation. And basically there, we only allow a hop-by-hop NAS to be placed below the top of stack label, so only at this position or at the active segment. And now a node that brings this NAS to the top must then move it one segment deeper after processing. So if we look at this stack, the select NAS is processed and popped because it's a select NAS anyway, and then we move the below forwarding label up or move the hop-by-hop NAS down. It's basically the same. And in the end, we receive this stack. And after that, we can, or if we get this stack, the next node can repeat the same. So now this has the advantage that the stack only has to hold one hop-by-hop NAS, and that mutable data is reflected in stack anywhere because we only have a single copy. And we also do not have to search for hop-by-hop NAS buried somewhere in the stack. So we know that if you're going from the top, we will find our hop-by-hop NAS pretty soon. But the problem is that M&A incapable nodes cannot deal with this. And also this does not follow the traditional MPLS push pop swap paradigm, but we have some kind of a reorder mechanism in this. So here you see an example of how this would look like. Note that this node now speaks MNA2, and basically the hop-by-hop NAS is updated by each node and moved down by one segment after forwarding. And this is, yes?
We have a question from Hao-Yu.
Ah, yeah, didn't see that. Yes.
Yeah,
please.
actually, you may talking about it, but it's related to slides 13. I think that's another question is now LSRB is capable of M&A, right? But if it's incapable of M&A processing, so the process of it will be just pop the top label, then it will expose the NAS as at the top of stack. But as specified in the specification, that's not allowed because LSRB is incapable of M&A. It will do nothing about that. And then the next step, when it's reached to LSRC, if it's indeed ISD capable, but it will see the top of stack is M&A stack, substack, that will violate the specification. How to solve that problem?
Well, the draft says that was a question, right?
Yeah, that's a question. Yeah.
Okay, so I think the RC or the draft said that if a M&A capable node, and that's LSRB here, for example, exposes a NAS to the top, which it does by popping the forwarding label after forwarding. So this is the packet before entering the switch. Then it also must pop the hop-by-hop NAS, and that's what happens here.
Oh, okay.
And then this packet, so below label 80, is forwarded to LSRC, which is not capable of M&A, just does the forwarding according to label 80, and then we can proceed with doing the hop-by-hop NAS at LSRD.
Okay, got it.
Okay, then back to the hop-by-hop NAS preservation. I think I explained this already. Yes, I did. And as I said, that's what we implemented. And we also implemented the hop-by-hop NAS replication before, but more on this later. So now we've seen the problem of mutable data, where we can only use the last 8 bits of an LSE, and that we can use hop-by-hop NAS preservation to keep the hop-by-hop data. But the last only works if all the nodes know M&A. Now, another approach to solve the mutable data problem is post-stack data. And this works because the post-stack is not hashed for ECMP, so we can use all data bits. And also the data is kept in one place, namely the post-stack, so we do not have to do some copy around mechanism. But here the question is if we can implement it efficiently. And for us, the challenge is, how do we get to the post stack? We have basically 2 or 3 options. We can jump over the MPLS stack if our device supports jumping, or we can use a look ahead function by just looking at the bottom of stack bit until we are at the end, or we have to parse the full MPLS stack. And a small teaser for our implementation, we are not capable of jumping during parsing, so therefore we have to parse the full stack. And that may sound not that promising, but for us on the Intel Tofino, it's not a problem to a certain depth. Yes, another question, Greg.
Yes. So we discussed it in our previous interim meetings. So post-stack data becomes, I would say, more interesting because of several technologies that use their own post-stack headers. Specifically, it's pseudowire control word. It's a DetNet control word. It's a ACH. It's a DetNet associated channel header, and it's a beer header. So effectively, in these cases, if and when there is so basically there are a lot of consideration, but the fact is that these post-stack headers are expected to follow immediately after their label stack element with their S-bit set. So then if any PSD applied to them, then they must follow their post-stack headers. So again, just looking for this magical bottom of the stack label stack element might not work. So basically, what you need to know is you need to know your label, because only based on a context of label, you can determine whether you have application post-stack header and what's the size of this post-stack header, because they are of different size. So it's either a 1-stack element, 2-stack element, or some arbitrary in case of beer. Thank you.
Thanks. Okay, then I will proceed to our operation modes. So with the previous knowledge, we now propose 3 different operation modes depending on the requirements to the nodes and the network actions we want to implement. And note that this does not require big changes in the M&A drafts, except for maybe the hop-by-hop NAS preservation concept, but it's rather an application of the current drafts. So first of all, we have the compatibility mode, and we implemented that with the hop-by-hop NAS replication. Therefore, we can have a mixture of M&A incapable and M&A capable nodes. There we have 2 submodes, one using in-stack data only, which is less restrictive to the readable label depth in our case, but we only have a few mutable data bits available and only in some circumstances. So therefore, applications or use cases here would be network actions that do not require mutable data, for example, the direct export feature of IOAM. Then the second submode is compatibility with ISD and PSD, or PSD only, depends. There we have more mutable data available in the post stack, but we have to get to the post stack somehow. So that's the challenge. And therefore also use cases would be, of course, network actions that require mutable data. And the third mode we propose is the greenfield mode. There we make use of the hop-by-hop NAS preservation concept, and therefore we can, for now, only have M&A capable nodes. For this node, we say that if we are going to do a greenfield deployment anyway, we just say that we require entropy labels. Therefore, we do not have to hash the stack, and we can have all data bits mutable in stack. So in this case, we have no need for PSD, for example, for the direct export feature. Therefore, use cases could be all of the above. Okay, now for some details on the implementation. Before I dive into that, short intro to P4. P4 is a high-level programming language to describe the data plane of switches. There we have a compiler that maps our P4 program onto the pipeline of a target. And that pipeline in P4 consists of a programmable parser, some control blocks, and a deparser. In those control blocks, we define our packet processing operations. there we make use of match action units, branching constructs, logical and simple arithmetic expressions. What we cannot do is loops. And if we have to loop over something, we have to do a recirculation. And in a recirculation, we traverse the pipeline once, send it back to the ingress, and can process it again. So now for the parsing of M&A. And you might have heard about my previous talk on the M&A header encoding. Basically, there I said that the different encodings are too complex to model them in a finite state machine, like the before parser uses one. And there I proposed different encodings. And at this point, thanks to the people and the discussion last time, because that really helped us pushing the implementation in the version we have now. And because now I know a little bit better, because in the implementation, we simply ignore the different encodings during parsing. So we parse all LSEs after the initial opcode into the encoding of a subsequent opcode. And then later during processing, we can decide whether we are looking at an opcode or at an AD-LSE. So an M&A or a NAS, which is in the packet like this, looks like this in the internal representation of our implementation. Yes, question? Stuart, please.
Yes, I'd like to do a reality check, if I may. Is P4 deployed in any production network at the moment, or any production platform? And if not, is it likely to be? Because I'm trying to make sure that we're designing this around the majority rather than an artifact of one particular implementation. Tony.
Stuart, you're asking two different questions. You first asked if there was existence proof. Yes, there is. Previous employer shipped a barefoot based box. You asked then about majority. No, it's very much in the minority.
Yes, so we are building in P4 to build a proof of concept. Of course, that doesn't mean that the draft has to be designed around P4 or something like that. It's just our experience we have in the implementation. So in the implementation, during the parsing, we push the parsed LSE on one of those three types of substacks in the internal P4 representation. And note that this is very P4 specific or specific to our implementation. So that's not something that has to be addressed in a draft or something. It's just background information about our experience. And we have to do this to apply the operations later then according to the placement in the stack and to emit the substacks in the correct order. There we have the active segment stack, which contains everything that's related to the current segment, so the forwarding label and the relevant NAS. We have the intermediate segment stack that holds labels and NAS of other segments. And those are labels we have to parse to get to the bottom of stack or to find a buried hop-by-hop NAS. They are parsed but not processed. And then finally, we have the persistent stack that holds post-stack data or hop-by-hop NAS located below. Now at P4, we have to fixate the maximum size of all of those stacks. And the space for the allocation there is limited. So we have to think about optimizing the size of those substacks to the requirements of our network. For example, if we know that we have long paths in the network, we should increase the size of the intermediate segment stack. Or if we know that we have many or large hop-by-hop actions, we should increase the persistent stack size. But we have to stay overall within the readable label depth, so that's a constraint for us. You can see now an overview of the assignment of labels to the corresponding substack according to the implemented mode. And here basically the active segment stack is always the same, like here and here. It contains the forwarding label and the relevant NAS. For the in-stack data only mode, the intermediate segment stack holds labels until the first hop-by-hop NAS is found, so this part here. But for the PSD mode, the intermediate stack holds the full remaining MPLS stack until the bottom of stack. So you see here that the intermediate stack has to be a lot bigger if we're doing PSD in our implementation. Then at the bottom, in this case, we find our hop-by-hop NAS, because as we have to be within the readable label depth for the whole stack for PSD here anyway, we can place a single hop-by-hop NAS at the bottom, and we do not need hop-by-hop NAS replication here. Then in contrast, for the greenfield mode, the intermediate stack only has to hold one label, and we do not require a persistent stack. So we can stop parsing quite early here, and we only have to check this part. And this makes, in our case, the greenfield mode the most efficient one regarding the readable label depth and the allocated header space. After we are then done with parsing, we get to the processing of the stack in the pipeline. And here one match action table for each LSE in a NAS is required, and such a table holds the opcodes and the network actions. And therefore, we need 16 tables for each scope. So 16 for the hop-by-hop scope, 16 for the select scope. And those tables are then applied sequentially. Now we ignore the different encodings during parsing. And in processing, we match on the network action length field for each LSE. So on this field here, where we have the value 1, and then execute an action that accesses the following number as AD encoded LSEs. And then those LSEs are skipped and not processed as opcodes. And that's how we get from this encoding back, or from the simplified encoding with only subsequent opcodes, back to the semantics of the original NAS. Now, another point is that the pipeline space is limited. So we can only fit n of those tables in the pipeline. Then we have to go into recirculation. And here you see a very high-level overview of the pipeline in P4 for the greenfield mode. There we have those different stages, and in each stage we apply n of these tables for the different scopes. So a packet here enters the pipeline, and the first n entries of the first NAS are processed. Then for the first NAS, we apply some trick on the Tofino to get it processed without a recirculation in the egress, but this only works for the first NAS, and I won't go into details here. So after that, we have to potentially recirculate at most twice if there's another NAS in our scope, or if there's a very large second NAS. And then finally, we do the hop-by-hop label preservation mechanism and forward the packet. And for the other modes, the pipeline looks very similar, but for PSD, we have another recirculation. So the concept is basically the same. There are differences in parsing the packets. Now you see here that in the first iteration, we can process a maximum or a fully sized NAS with 60 network actions without having to recirculate. And maybe compared to IPv6 extension headers, because that was the motivation at the beginning, we can, depending on the device, do only like 3 extension headers without recirculation. So this is compared to that, it works. And also note that the recirculations here are only required in the worst case. So we can do many network actions if we place them accordingly. So now, as I teased already, the post-stack implementation brings some more requirements for P4. And first of all, for us, everything must be within the readable label depth. So we cannot jump in parsing, but that's not a problem for us on the Tofino. So we can just parse the full stack in line rate. And as I said before, other forwarding engines have their ways to find to the bottom of stack. Another constraint for us is that we have to stay within the distribution of those substacks. So for example, here we say that there can be 16 LSEs between the active segment and the bottom of stack. But of course, we can move the sizes around as long as we stay within the overall readable label depth. We just have to keep this in mind. A disadvantage here is that PSD processing increases the number of recirculations, but in the future, we maybe can optimize this. Okay, so one thing we asked ourselves during implementation is, if we are doing the compatibility mode with PSD in P4, that means for us that we have to have the whole MPLS stick in readable label depth. So therefore, we do not need copies of the hop-by-hop NAS in the stack, and we can place a single NAS at the bottom of the stack. And there we can indicate the post-stack data. So that also means that we can place all the hop-by-hop network actions and the data in the post-stack, and that we can shrink the size of the hop-by-hop NAS to 2 LSEs in this case, 1 LSE if we could use the TTL, but we already talked about that. And for us, this would reduce the number of recirculations in the implementation. So yes, question for discussion. Can we use the hop-by-hop NAS to only indicate PSD, or is there a requirement to have in-stack data actions in parallel with post-stack actions? Or can we say that we're moving everything to PSD?
So as we've discussed, the working group has no requirements for PSD at this time.
Yeah, one question on this slide in regards to readable label depth. If you recirculate the packet, wouldn't the readable label depth increase? And if so, why wouldn't it improve the the in-stack approach versus the post-stack?
For the first question, it doesn't increase the readable label depth because we can parse the full stack at once. And on each recirculation, we can parse the full stack again. So that doesn't make a difference for us. Of course, it could be increased if we do the select NAS in the first iteration and then pop it. And then the stack is a bit smaller and we can go deeper. But that's a special case.
That's what I was thinking. You advance and then you do another parsing. But yeah, that's what I was. I got that feedback. Yeah, thanks.
Yes, and what was the second question again?
Yeah, if the readable label depth, if it increases, then it will benefit the in-stack approach. But based on your implementation, the readable label depth does not improve, even though you can recirculate the packet.
Yes, that's correct.
So I think each time of the recirculation will effectively halve the throughput. So that really should be avoided, which means for the single pass processing, that might be actually a RLD limitation for this kind of hardware. So we should try the best to limit the size to make it to ensure it can be processed in single pass without to avoid any recirculation. That's one point. Another point is even though this Torfino hardware is actually rarely used, it's never widely used, but the basic parsing logic is also adopted by the Broadcom's ASICs, switch ASICs. So they use a similar approach, so they will face a similar problem. And of course, there's other type of devices based on network processor, which is totally software programmable. But on that, I don't think their parser is more efficient than ASICs, because ASICs actually take advantage of all the parallel processing. It can actually parse a header in a single state machine clock cycle. So, but if you do that in a pure software way, that will obviously it will take more cycles. So I can envision the performance will be much worse than that in ASIC hardware. So I really think we, for any encoding style, actually we should consider how we can implement that. How they behave in different kind of hardware. And thank you very much for actually doing this work to at least provide some experience on this one available hardware, but we may also need to see how it behaves in other type of hardware. Thank you.
Thank you. Okay, so finally, for some implemented example network action, basically we implemented some kind of a simplified version of a path tracing mechanism in the context of IOAM. So it's not IOAM. We just wanted to build a proof of concept that we can access all the fields, match on the correct fields, and do something with it. So the goal of our example network action was to collect the node ID of each traversed node and evaluate the path at the tail end node. So basically simplified. And yes, Greg, before I do a deep dive.
Yes, actually, about the simplified version in the context of in situ OAM. So yes, path tracing have been proposed for IPv6 only. So path tracing has not been proposed for MPLS network. And I think that probably it's better if we not consider it, because there is even less, in my opinion, ground to discuss the applicability of path tracing in MPLS network. Thank you.
Yes, I do not mean that we have to implement path tracing or something like that. It's just a proof of concept that the pipeline processing works. Of course, you can do anything else with that. That was just the simplest thing we could do with those actions. And there's another question. Yes, please. Rakesh? Okay, probably not. Then I will just continue. Okay, so we designed the network action. Okay, now maybe?
Sorry, I was talking on mute. Sorry. There is a draft on path tracing for MPLS. I'll put the link to the draft in the chat.
Oh, thanks. Okay. Okay, so we designed the network action like this, that we have an opcode to indicate simplified IOAM. Then we do matching on the flags, and there we say that each flag indicates what metric we want to collect. For example, we want to do node ID collection, then we set this bit. Then we reserve AD LSEs in this case. So let's say we reserve 5 entries. That means that transit nodes do not have to add LSEs. And then we treat the mutable data field here as an index to indicate to transit nodes where they have to write their data in the ancillary data. So if there's a 0, the transit node inputs its data in entry 0 and increments the index by 1. And then finally, the data is written into here. And that's what we implemented actually on the Intel Tofino. And there we run without a recirculation at 100 gigabit per second. And note that this is the in-stack data only version here. So therefore, the hop-by-hop scope needs to be at the bottom. But of course, we can move this to the other modes. And what you see here is basically the packet enters node A, sees opcode 42, node ID metric collection flag, and index 0. Then therefore, it writes its node ID, let's say A, into the data field, forwards the packet, and increments the index. Node B does the same, or every node does the same, and at the end, we have our path. Okay, so that was the in-stack data version. Here you see the same with the greenfield mode, and note that here we can make use of a single AD LSE because we have more mutable data, and that we can use the index to write or to specify the offset where to write it. And here the overall stack looks a lot more compact, and we make use of the hop-by-hop NAS preservation concept, where we just move the hop-by-hop NAS down, and this also works. Post-stack data works similar, so it's the same concept as this, but of course the data is in post-stack and not here in the AD LSE. So now that brings me to my conclusion. So in this work, we analyzed the requirements for network actions, and therefore we proposed 3 operational modes for deploying M&A in a network. So namely the compatibility mode with ISD, ISD and PSD, and the greenfield mode. And we implemented all 3 modes in P4 on the Intel Tofino 1, running at line rate of 100 gigabit per second. And by the way, some nice side products of this project are that we have a Python library where you can assemble and send M&A packets, and we have a Wireshark dissector extension for visualizing that M&A traffic. So now one of the initial questions was if the IETF M&A encoding can be implemented efficiently on hardware. And we say, yes, the encoding works, but depending on the size and distribution of the substacks, we have to go into recirculation. But in the best case, we can do 60 network actions without having to recirculate. The challenge in an implementation lies in mutable data with in-stack and the hop-by-hop NAS replication. If we are not doing this, then post-stack brings some harsh requirements, at least in our case, namely that we have to get to the bottom of stack. And finally, here you have an overview, which of the modes one can use depending on the requirement. So if you have only M&A capable nodes, we say that you can go for the greenfield mode because it's the most efficient one in this case. In the P4 case, if you can accommodate the entire header stack in the readable label depth, you can do post-stack data, potentially need more recirculations, and if not, you can do in-stack data only. And now for some future work, we still want to optimize the implementation, meaning we have ideas how to reduce the number of recirculations, but we have to test it out. And also on the Intel Tofino 2, we expect better performance. And also we have some ideas how we can make the greenfield mode, so the hop-by-hop NAS preservation mode, compatible with M&A incapable nodes, but we have to think about this first. Then we want to extend the range of implemented network actions, for example, the MPLS in-band performance measurement draft right now, or the direct export IOM option. And we also have currently a paper about our findings as work in progress. So if you want to have maybe a specific network action implemented and see how if it works, or if you want to join in on writing the paper, we are open for collaborations. Just reach out to me. So thanks for your time. Now I'm open for another round of discussion, and maybe to get the discussion started, you have an overview of the 3 different operation modes and the requirements. And now my initial question is, what do you think about the modes? Do you think they are feasible, especially with the PSD requirement? Thank you.
Can you go back to slides 29?
This one?
Oh yeah. Let me see. Okay. What mode is this? You mentioned 3 different mode compatibility and
yes, this is the compatibility mode using in-stack data only.
Oh, okay. So you also said here is this substack must be at the bottom of stack, right?
Yes.
If that's the case, and it actually doesn't matter if it's a in stack or post stack. It can be done also in post stack, and then without any limitation on the format, right? Because if it must be at this location, and you force it into in stack, you basically add some artificial limitation on that. If at first place, if it must be at the bottom stack, it can be PSD and format free. So that's my comments, right?
Yes, that's true, and that's also the intention behind the slide, because if we are not placing the hop-by-hop NAS at the bottom, it means that we need to have copies in the stack, because else the other nodes wouldn't get the hop-by-hop NAS with the problem I've explained on the slide before. This means we have to place it at the bottom, and you see that it's not that efficient. And that's what brings this mode, or the PSD mode, which is similar. There we can make use of mutable data. So I'd say in-stack data only is, as you've already discussed a lot, not really suitable for mutable data. But it could be implemented if you really want to.
Okay.
Okay, then Tony is next in the queue.
Talking on mute. So a couple points. First, you mentioned you had some Python and some Wireshark stuff that you've done. If you would be willing to share that, that would be most appreciative. I'm sure that testing folks and development folks would be very interested in playing with that. On your last slide, you raised greenfield mode, and that's not possible, right? The internet cannot be swapped out. There are no flag days, so we don't get to do that. And compatibility mode with ISD and PSD, again, we have not accepted that we are going to do PSD. So that's not even an interesting case right yet. So then we're really looking only at ISD only.
Yes, thanks for your input. Actually, yes, the greenfield mode only would work if we have M&A capable nodes, but we have some ideas how we could move that to M&A incapable nodes as well, but we have to test it around a bit. So I will give notice on the mailing list as soon as I know more about that. And for the ISD and PSD mode, I don't want to say that we should do this or that it should be decided to do this. It's just current state. it would be possible, has some requirements to us. Yes. Okay, done. Next one in the queue.
Yeah, thank you very much for all this work. It's very interesting. And my first question is about the path tracing case. Can you go back to that page? Yeah,
This
in this
one
case,
or that slide before?
This one, yes. So in this case, you put hop by hop NAS in the end of the stack, but will this cause an ILD issue for some nodes? They cannot pass or they cannot reach this hop by hop NAS because it's deep in the stack.
Yes, that's correct. And that's also the motivation why mutable data in stack is a bad idea. Because the other option would be to have another hop by hop NAS like somewhere above here.
Yeah.
But if you're doing mutable data, then you would pop that hop by hop NAS somewhere in between. So let's say here. And then you have the issue from before that you have to copy the mutable data down, but the copy is out of reach. So I know that this is not feasible for most implementations, but as I said before, if you want to do in-stack data only with mutable data, you would have to do it like this. Or you find some way to solve the copy problem.
Yeah, I agree with this analysis. And another case I'd like to mention is the size of the data, even if it is not mutable, if it needs to be hop by hop processed, if you put it in the label stack, it will also need to be replicated several times, and you can impact the encapsulation efficiency, as you do not have much space for the normal forwarding labels in the label stack. Have you considered that case? So that maybe the size of the data can be something need to be considered when you decide to whether use ISD or PSD for a specific type of action. That is not just mutable or not, but also the size can be something to be considered in this choice.
Yes, of course. It all relies on the capability of readable label depth on your nodes or of your nodes.
Yes, especially if we want to consider some legacy nodes, if they want to do the normal forwarding, right? And another thing is about the last page, you do the comparison between the three modes.
Mm-hmm.
And what I'd like to say that in the green mode, actually, you are creating something not compatible with existing MPLS. Then do we still need to follow the label stack format or the behavior introduced by MPLS? It's just a new protocol, to my understanding.
Yes, actually, that's why it's called the greenfield mode. It's just an example of how efficient it could be if we are not backward compatible. But the point is that if our idea works to also get this mode working with M&A incapable nodes, then we could have mutable data in stack without that copy problem. Then, of course, if you do not have entropy labels, you still have 8 bits per LSE only mutable, but you can have only one hop by hop NAS with mutable data in stack. But as I said, we have to find out if that works. That's just our current state of the art.
Yeah, I think it only makes sense if it can be compatible or interoperable with existing MPLS nodes. Otherwise, we can do the protocol extension without these limitations of the existing MPLS format, right?
That's a good point, yes.
Yeah, thank you.
Okay, we are past the mark for today's meeting, and I want to reiterate my my thank. I'm glad that you presented this, Fabian, and this was very great work. thank you for sharing your experiences. The slides, I have left a link where you can upload the slides. If you can take a look at the chat and please propose the slides, and they will be documented so everybody can have access to it.
Yes, I will do that after the meeting now. And also for the Python and Wireshark libraries, I have to clean them up a bit more, honestly, but I'll just reach out to the mailing list and push them to Git or somewhere that you can have a look at that.
Link would work great.
Yes.
If you can leave the URL in the slides itself, that would, people would have access to it, towards the end, last slide maybe.
Yes, I'll add it, but as I said, I have to clean it up a bit, so might take a day.
If you want to send the URL to the mailing list separately, that's fine too.
I can do also both, so doesn't really matter.
Sure. Thank you so much again, and I'll send towards my co-chairs if they want to ask any further questions before we adjourn. Directed to my co-chairs.
So no question from my side, but I think it was really a great job. Thanks for the input.
Thanks.
Thank you, Fabian, and your entire team for helping. We invite you to participate actively as part of the working group. Thank you very much.
Yeah.
Thank you.
Okay, have a good day. Bye.
Have a good day.
Thank you. Bye.